Hello and welcome. My name is Sage. I'm currently a senior, and this is episode 1 of my pre-calculus enrichment series. That symbol on the right, that's a series in math, but you will see that later. And so today is going to be about understanding domain. I'm planning on making this like a 2-part series, so you will see a real-world application in the next episode. Or just the next part. But today is more about just easing into the topic of domain and why it's important, how we find it, and all of that. So let's just get started. I'm hoping that with these 2 parts I'm doing, you will be familiar with functions, specifically root, rational polynomial, inequalities, types of numbers, prime, real, integer, stuff like that. And interval notation. So that's when we use brackets and parentheses and infinities to sort of express domain and range. I'm hoping you will be able to recognize number sets, identify domain and range, explain the importance of domain and range in context, and determine domain and range algebraically and graphically. So this is like for the 2 parts, but I want to start out with a tour of a mathematical storage room. I don't know if these exist. I would sure like to see one if they do, but this is kind of my creation of what that might look like. And so we see some boxes here. We have whole numbers, even numbers, prime numbers, integers, real numbers. So lots of boxes. And there are more in the back, but you can't see them. Neither can I. And so these are kind of collections of numbers. And in math, we call those sets. And the reason that we talk about sets is because sets are what sort of define functions. And to understand domain and range, we have to understand how functions work. So let's look at an example. Like I said, functions relate the elements of one set to the elements of another. So each of these boxes has a collection of numbers in there, and you can pull out some of those numbers and plug them into an equation, a function, and you'll end up getting some outputs that go with another set. So here's kind of a simple graphical example. We have y equals 2x, it's standing on its own, and I pulled out my set of integers. And so I picked some random values. I have -1, 0, and 3, and I plug those in, and these are the results I get. So right off the top of my head, we can kind of see how all 3 of these numbers, they are integers, but they're also real numbers, right? And so kind of what I figured was that if I plug in these integer values into my function, I'm going to get real numbers. I mean, I knew that for a fact because you can look at it and see that we're not going to get any numbers that are, complex or have eyes and things that aren't allowed. So I chose an output set of real numbers, and that is true. It's also, you have an output set of integers as well, not all the integers, but some of them. So it's really just about taking one set and then taking those elements, relating it to another set. But this is if I'm just, given a function, and in this case, I chose an input set or a domain of integers and ended up getting real numbers. That's also kind of a choice that I made. But we can kind of change it up too and say, there's an actual context to this function. So I'm a big fan of cookies, and here's my cookie function. N represents the number of cookies that I buy, and C will be the total cost of my cookie purchase. And so now the way that we're relating our sets is kind of changing. So I can't have negative cookies. So now I have to adjust my integer set, and I want to make n greater than or equal to 1. So that's kind of a set on its own. You know, just saying that n is a subset of positive integers that are greater than or equal to 1. You know, that doesn't really have a nice simple name like prime numbers or whole numbers, but it's still a set, and it's a set that we can use to plug into a function and then get an output set. And you'll notice that if I plug in this little set that I have within my integer set, that I've made that restriction according to the context, if I plug that in, I'm going to get even numbers. And, you know, that's a pretty name, even numbers. It's not so ugly as my inequality one, but it's a subset as well. It's a subset of my original real numbers output set that I chose in the beginning. And so you're kind of seeing how if we take kind of a regular equation that standing on its own has no meaning, and we can choose whatever domain we want and get whatever range we want, you know, if I actually put a context into it, now I'm starting to see that I have to make some domain restrictions. I have to define some sets, and that might go ahead and limit the range or the outputs that I'm able to get out of it. And so I'm throwing out a lot of vocabulary here, but let's go ahead and actually define some things. So what are domain and range? Domain, as you could probably tell by what I was saying, domain is just the input set. It's the set of numbers that we plug into our function. In the last example, n is greater than or equal to 1 was my input set. My range is going to be my output set. And that's just what I get when I apply my domain to the function. It's the set of numbers that I get out of that. In the last example, we ended up getting even numbers. And I put this real numbers, and it's a big star on this screen. And that's because typically in calculus, we're working with real numbers. We want outputs that are real numbers. And our range is usually going to be a subset of those real numbers. So with that said, this is going to be our example for today, and then you can come back to the next video and we can do some little more in-depth analysis of what we're talking about. And so how would you find the domain of each function? So if you're just given a function and there's no context to it, it is what it is. This is kind of the thought process you want to go through. You want to think of domain as the inputs that give valid outputs, and the range is going to be what our actual outputs are when we apply those inputs. And like I said in the last slide, those outputs are going to be kind of a subset of real numbers. They may be real numbers, maybe that is our range, but typically, you know, depending on the function, and we'll see that in the example, usually it's just going to be like a box within our real number box. And I put quotations around valid because the meaning of valid is going to change depending on if we are just looking at the function by itself or if there's a context to it. So now that we've kind of done that briefing, let's go ahead and get into part A here. So we're given kind of a typical quadratic equation, and this is the function we'll be working with in the next video. But all right, so according to this box up here, let's kind of go through our process. I'll walk you through it. So the domain is going to be the inputs that give valid outputs. So I have to look at this function and think, what can I plug in here to get real numbers for S? And because it's a polynomial, just kind of in the definition of that function, our domain is going to be from negative infinity to positive infinity. And we can see that any real number for t is going to give a real number for s. So we have that, and then our range is going to be what we actually get from that domain. And sure enough, it's actually going to be a subset of real numbers. You might be tempted to think that it's negative infinity to positive infinity, but we have to understand the nature of this function. And I have a graph here to show you that. This is a downward facing parabola. So we have a vertex at the top. And so our range is going to have a maximum value. We can see that it does go to negative infinity in the y direction, but it's going to have that maximum value at the vertex that is going to restrict our range. So when we actually plug in our domain, the range we're going to get is from negative infinity to that maximum value, which is, in this case, 3.563. And that's included, so I use a bracket. And there's that function. And I'm going to go ahead and move on to part B. This is a rational function. You looked at that in Math 3. And so we're going to go through the same process. We're going to ask ourselves, what are the x values, the inputs that are going to give us valid outputs? In this case, it's not a polynomial, so we have to look for problem areas. You know, what are x values that would generate some non-real outputs or some invalid outputs? And so you'll recall that when we're working with rational functions, we have vertical asymptotes because we can't divide any number in the numerator here by 0. And I'm actually going to mention that more in a later video, so I'll explain that. But you know, just recalling vertical asymptotes. So I would say the bottom of this fraction cannot equal 0. And so then I see what that's about, and it looks like our vertical asymptote is going to be x equals 1. Because when I plug in 1, I get a denominator of 0, and that can't work. So that's going to break up our domain a little bit. And so it's really going to be negative infinity to 1. 1 is invalid, not included. Union 1 to infinity. Okay, so we've removed our trouble spot from the domain. And so when we plug this in, we should get all valid outputs, right? Negative infinity to infinity. Not quite, I'm sorry. But when we're looking at rational functions, we have to take into account that in behavior, what's happening to the graph when we're plugging in super big or super small numbers. And so you should remember like the mnemonic BOBO BOTN EATS DC. I don't really use that, but in this case, we're looking at exponents that are the same. So you pay attention to the degree on the top and bottom when you want to find, you know, any breaks in the range of this function. So looking at horizontal asymptotes, we see that the degree on the top is the same as the degree on the bottom. BOBO BOTN tells us to DC, divide coefficients. And so we get a horizontal asymptote of y equals 1. And you remember that horizontal asymptotes are what affect range. And like I said, I'll go into more detail about that in a later video. But for now, we're just kind of using some information we've picked up from the last math class. And so it's going to be the same as our domain for our range because of that asymptote. Put that in interval notation. Okay. This is our final example. And so I am actually just going to kind of set this up, but starting with domain, going a little faster here. What's going to give us a valid output? We have to look for problem areas. And our problem area is going to be right under the square root because we can't take the square root of a negative number. So our domain, x plus 7, we're going to take everything that's under the square root. X plus 7 has to be greater than or equal to 0 because that's just kind of, you know, how we would make sure that we don't get any negative numbers under the square roots. X is going to be greater than or equal to -7 if we solve that inequality. And that's not in interval notation, but I'm just going to leave that right there. Okay. So we've removed some problems with the domain, but what are the actual outputs we're going to get? And we can see that our smallest value when we plug in our domain is going to be -7, and that's a y value of 0. So that means our range is going to go from 0 to infinity because the smallest y value we can get from our range is 0, and then it's just going to go off into the distance, as you can see with the graph. So yeah, okay. This is going to be it for this video, and I hope you tune into the next one. So thank you very much, and math is fun.